Hello everyone and welcome to another edition of Nanotalks. This Nanotalk is a recording of a user webinar we did with Dr. Michele Conroy, who uses in-situ biasing to investigate phase changes in highly conductive polymers and ferroelectric oxides. Now we will switch to the recording. The presentation starts after a short introduction of the speaker, and after the presentation we will have a Q&A with the audience. So please enjoy this Nano talk. And of course, a very warm welcome to our presenter. Today we have our second user webinar on Lightning, on our Lightning system, and this time it's Shelly. Dr. Shelly Conroy is an SFI Analog Device Research Fellow at the University of Limerick. Her current research is focused on multi-ferroic domain wall dynamics and utilizing in-situ microscopy to investigate these 2D entities. She was just awarded a Royal Society University Research Fellow PI grant, where she will be conducting thin film growth of improper ferroelectric oxides for conducting domain wall-based devices. Again, Shelly will be utilizing in-situ TEM to study their dynamics. Before joining the University of Limerick, Dr. Conroy was a staff scientist at Pacific Northwest National Laboratory, specializing in situ liquid cell, heating, and cryo-TM. So she has some experience in situ. She completed her PhD at Tyndall National Institute in thin film growth for optoelectronic materials and in situ heating TM. I want to switch to our presenter, to Michele. Great.
Perfect.
So please go ahead, enjoy.
Thanks a lot for the kind introduction. So today's talk is going to be divided into two. So this first part is going to be conductive polymers, and the second part then is the major project with my group that's led by Professor Isha Bangert, so ferroelectric domain walls. And I hope I get across to you how important it was for us to be able to do in situ biasing, and specifically that the stage was stable. Otherwise, we couldn't capture some of this really interesting physics. So we are in the lovely west coast of Ireland at the University of Limerick. We're housed within the relatively new Brunel Institute. About 2016 is when it kicked off. We work within Professor Isha Bangert's group. So that's some of the group there, but because of the current situation, we don't have a new updated group photo. I personally use the FIB to make some of my samples. So I'll show you that later in the talk, specifically for in-situ biasing and heating. And we're very lucky also at UL that we have a double corrected Titan Themis. So as I was saying, we have the Titan Themis cubed, that's monochromated, image corrected, probe corrected. This talk, I'm going to show you some of the results using the GATAN 1 view and also the GATAN K2. We're also working with Berkeley National Lab, where we use also the GATAN K3. We have STEM Xbox as well for quadrants EDX detector, and for us some results will show also with EELS as well, because the great thing also about some of the advancements with the spectrometers is that we can get down to very, very small energy resolution. So in terms of DENS and in situ, we have all of the holders. So the two main ones that I work on will be the Lightning. So do the biasing and heating, and then the other holder as well that I use at the moment is the stream holder, so more biasing, and that's in collaboration with Professor Kevin Ryan's group and Dr. Hugh Gainey as well. So to get into, hopefully my slide works, yeah. Okay, so starting off the first material. So the first thing I'm going to talk to you about is material I am not that's not my experience in, which is a polymer. So amorphous polymer, very much an oxide or metals kind of background. But what I think like that always kind of happens in a good start of a collaboration is just chat in an office or down a hallway or at a conference. So hopefully in real life we can get back to that. Talking to senior postdoc in Michele Scanlon's group at the University of Limerick, Alonso, and I think he's on this call today. So hopefully if there's some questions about this material, because again, not my background, he can answer that possibly. But basically we talked to Alonso and he was saying, oh, within, Michele's group, that they're making this really cool conductive polymer. And it's made in the way that it's formed at the interface of, very simplistically, an oil and water interface. And what I was really surprised about was that how conductive it was. And so for us, we're very focused on band structure measurements and band gap measurements via electron spectroscopy. So I want to get my hands on this and also questioning, is it really amorphous? So we moved on from that and I took it in the microscope. We had a look, and when you start getting magging up and up or being able to see better resolution, you can see it's actually made of interwoven kind of tight knit fibers. And from what I can see, down to around 5 nanometers, possibly even less, but that's further studies. Then we took that, and this is really just to give background of, this is very conductive, and it's not behaving like, let's say, a normal polymer. And by that I mean that there is some filling of the density of states. You don't need to, I guess, understand that, but it's pretty much acting like a metal, which is very strange for an amorphous polymer. So we conducted some low loss yields, and this is in collaboration with Sergei Lopitan at KAUST and Professor Benoit at KAUST. And then we were able to show that there is this kind of increase in density of states right down at the 0 loss peak. And also just to confirm that it's not just a once-off, we took several measurements and also repeated those measurements to show as well that there's not this degradation of the material. So it's not the beam inducing this, it truly is the material itself. So we now need to move on to doing some density functional theory calculations. So excuse my little model within the figure there at E, but basically you get this, what we believe is this kind of curvature and a bending of that conduction band to fill up those density states. So anyway, getting back to the in situ, so I went and annoyed Alonso and said, okay, well, this would be really cool to kind of go, what happens when you go through breakdown? Because that's really my previous work, my PhD was looking at breakdown as well of electronic materials. And Alonso then conducted this in that he increased the applied voltage much higher than you normally would want to. And you could see this beautiful line forming between the contacts. And in this case, he was using, I believe, copper wires. And so we thought, okay, that's really, really cool. What is happening there? And then even if, let's say, you put down this PDOT, the thin film of this polymer down, even in lots of different ways, you always form this golden region. And so just to bear in mind at the start, the material itself is what I call it 2D. It easily adheres to any material, so it was easier to put this down on top of the contacts. There's no other sample preparation. So we said, okay, well, this is really great, but we're at the light microscopy resolution, and also we can't really understand what's happening structurally. We can just visually see there's something changing. So we went to in situ biasing. And using what we call now Rob Lahan, who is in Michele's group, we tried all these different methods to get the polymer down. So in the second part of the talk, I'll talk about how to make fib lamella, but this is an amorphous polymer. I cannot fib this, otherwise I will destroy the material. So do the little video again, hopefully. Rob and Alonso would float the little polymer flakes on top of water, and then you're able to bring down the chip upside down and then bring it, of course, back upright, and it was able to adhere then to the contacts in the chip itself. So in the figure up on the left, you can kind of see that grainy pattern that is on the MEMS chip is actually those larger fibers of the PDOT material. So you can see it lies nice and flat over the chip itself. So in this case, we used, just for background, we used a 4 heating, 2 contacts, or 2 biasing type of MEMS chip. Okay, so then after a lot of work playing with the different types of applied voltage, we were able to capture that phase transformation from amorphous to crystalline. But not only that, we're able to capture the initial nucleation stuff. And that's really what I wanted to get at. And so it's an experience with a wonderful group, Professor Jim Diorio, Pacific Northwest National Lab, and that's really what they're always looking at. What happens at the start? Because the crystal growth is really interesting, but really what's the physics that's happening right at the start of the formation of these little nucleation particles. But to emphasize how important it is that we have a really stable holder and also the chip, and then also the camera and the frame rate as well. So you can see here frame 1, I show that was one of the ones where you start seeing these like little dense region we're calling a pre-nucleation kind of cluster, or nucleation cluster. And then frame 3, you can start seeing 3 of them, and then by frame 12, there's several of them. But to put that in context, that was 12 frames a second. And that's not even as fast as we can go, of course. But in this case, because it's amorphous, we wanted to try to get as much information as possible. So we did 4K by 4K. This is what worked for us. I believe if we use perhaps the direct electron detector, which we can, of course, on term the K2, and we might be able to use less pixels and maybe get a bit more frames in there. Okay, so then that was great. So we captured that. But we also want to look at the crystal growth as well. So what's fantastic about the holder, of course, is that we can also watch the IV curve at the same time. And now with the newer software, the Impulse software, we'll be able to watch that live. So this is some of the older results we got before we started using the Impulse software. Okay, so then the next step then, of course, we have these nucleation clusters. So then what happens? So because we can see that after a certain point, we form these nice stable crystals, but how do those crystals form? So from what we can see at the start is that it looks like some form of attachment mechanism, and it does look like Oswald ripening, but we've yet to fully confirm that, so that's our next step. Okay, so then, so what we wanted to do is we did several experiments to repeat this so that we always get to be able to say, okay, this is definitely happening over time, it's not a once-off. We can, of course, then look at the FFT. We also did it where we looked I did SA as well during to watch any change, of course, in diffraction spots, but really it's more important for us what we can see is that getting down to the atomic resolution so we can understand what's happening. The next step in our analysis then will be taking all of these frames, because one of these videos is 1.2 terabytes, so it's a lot of information, and being able to see can we then quantify using open access software. There's really some great stuff out there, especially from the cryo TEM community, and to understand is there a preferred crystal growth mechanism. There definitely seems like there is, and then also what kind of defects are within those crystals that are formed. And again, just to re-emphasize, it's really, really important to get the right ramp and also, of course, the MEMS chip stability, and then the right frames per second. So this is an example of one of the first experiments where it's great. We can see that it forms crystals, but really we can't get anything out of that experiment besides saying, great, we formed crystals during the biosyn. Okay, so for the first part of the talk, the conclusion, I suppose, is sample preparation is key. It seems like it's a really easy technique, which it luckily is to prepare these type of materials, but it was just the start trying to figure out how to do that without getting a short, of course, in the experiments. Fast camera, we're lucky we do have fast cameras here, otherwise, as I was showing, we wouldn't have captured that nucleation step. And the slow, of course, again, the slow ramp. And then, so from that, when I started seeing those initial experiments, I actually went to talk to Analog Devices, because I know that there's some work in breakdown of polymers that are used for isolation devices. And so with that, and from those initial results, I was very lucky that SFI, Science Foundation Ireland, and Analog Devices funded my research fellowship. And that's in collaboration with the Marie Curie Fellow that is linked within Professor Ishi Banger's group, Professor Sombel. So this is then, I'm starting to work now on non-conductive polymers and looking at how they break down as well and what phase changes happen there. Okay, so then acknowledgements with that. So Michele Scanlon's, of course, his group and the EU ERC funded project he has as PI. Alonso there, that is the PDOT wizard, and of course Rob Lahan as well, PhD student, is also the PDOT wizard. And then my previous collaborator, Professor Boonwi Kaust and Sergei Lopitan Kaust, and Sambel as well. Okay, getting to the next bit, which I'm very excited about, because as I think Olaf was saying, that I get to keep working on this for the next 5 years. So this is a US Ireland SFI NSF funded project called Domain Walls for Agile Nano-Electronics. This is where there's 3 PIs, so Professor Shibanger, Professor Marty Gregg up at Queen's University Belfast, and Professor Alexi Brueggemann at Nebraska Lincoln. The EM side, so the microscopy side, definitely grew legs, and I got very, very lucky with some of the collaborators after a lot of talking to them and everything. So the great group up in AML, and the ultramicroscopy group led by Professor Lewis Jones, SuperSTEM at Quinton Ramas for the electron spectroscopy and also the imaging as well. And then the Molecular Foundry with Jim Sufton and Colin Ophis for 40 STEM, and I'll talk to you about that and why that's really important as well in a minute. And again, KAUST as well, to start working on the DPC, and again linked with Sergei Lopitan. So why domain walls? Don't need to understand really ferroelectrics for this talk. What's really cool, I think, about domain walls and what sets them apart from, let's say, the other 2D materials is that they're agile and dynamic. So I like to think about it. So when I walk down, let's say, and I see the fabs and analog devices or any of these other companies, imagine if you could have all of your devices as not fixed components of hardware, that you as the end user could draw your circuitry. And so ferroelectric domain walls that are conducting and insulating allow the user to do that. But really, we're at the infancy of this whole field. So we want to be able to use this because it has so many promising possible applications. There's different chemistry at the wall, magnetic behaviors, not just electrical, coursing and conductivity, and so many of the things we don't even understand at the moment. So what's different about our approach, because there's a lot of people working great on ferroelectric domain walls, is that we really are focusing on proper ferroelectric single crystals rather than thin films at the moment. And then the other thing is that we're trying to draw and create them and then move them. So instead of trying to, let's say, form a thin film that already has a network of domain walls, actually being able to cycle that. So again, like the Etch-a-Sketch, you draw your circuitry and then you erase it, draw it again, and then on top of that, you're able to then move those domain walls. So for this talk, the fib lamella as well, I think of it as the single crystal. And then I have the whole network of domains and domain walls, so I don't need to think outside of the bulk material. The bulk material itself is the fib lamella, and the fib lamella is, let's say, a prototype device. So how they're made, so what was previously done at Queen's University Belfast is taking Professor Roger Watmore, now at Imperial College London, his material called copper chlorine borosite, and then they were able to show that just by pressing down, because it's a ferroelectric that's also a ferroelastic, they were able to produce this beautiful network of domain walls. And in this initial paper, then they were able to show that from CFM measurements, so conducting AFM, that there's these domain walls can be either neutral, so no change across the wall in terms of conductivity, or that they're also increase in conductivity or decrease, so conducting or an insulating wall. Okay, so then what I think is really, really cool is then showing how easily they can move. So the video, the light microscopy video on the left is from Joseph and Professor Marty Gregg's group up in Queen's, where he applied the bias and he's able to move that domain wall back and forth cyclically. So it also never gets pinned. So it's really important also for devices. Any of these domain wall based ones, if it gets pinned, that's the end of the device. So we're able to just move it back and forth and not hurt the material. So then I'm still a TEM person. So I take my material and then I need to make a TEM lamella. So I put it into the SEM fib, and I could see just under the SEM probe itself. And if you think about an electron probe as really, it's also an applied electric field. Then also with that, you're able to move those domain walls really easily, which is very unusual, not expected at all. Okay, so I'll get back to why and why that's interesting about the moving walls in terms of electron beam. But first, to talk about the material. So it is an improper ferroelectric. Again, that's not vitally important about the material itself, because we see that this type of behavior goes across all of the bore sites. So think of this material as a network of boron and oxygen, and then you can replace the metal and replace the halogen. By replacing those, you can also possibly induce other types of ferroic properties, perhaps also magnetism. But for this talk, we're going to focus on copper chlorine borosite. So why is it improper? So for this, you just think really simplistically, and I hope that diagram on the left kind of shows that. So it's from Ray's paper from the previous slide. So let's leave a perfect cube, and then at the high temperature, you go down to the lower temperature, which is room temperature for us, and you get a shearing of the unit cell. That shearing then results in displacement of the atoms within the unit cell, and then that displacement results in the polarization, and thus the ferroelectricity. That's all you need to remember. There's a shearing, that shearing turns into that displacement of the atomic columns. But we need to map out those atomic displacements, because we're not actually changing the chemistry, we're just changing displacements, and those displacements then result in whether something is conductive or insulating. Okay, so first took the material, and this is in situ heating and diffraction mode, of course, and hopefully you can see that you get the low temperature, it's nice and cubic, and then you get that shearing, like in that kind of little schematic I have there. And then if I hopefully play this again, all right, yeah. So at the low temperature, you get this kind of first sublattice you can kind of see, and then you get these extra superlattice spots, and those superlattice spots are then at the lower temperature. So we needed to understand, although this is really great to get this diffraction information, actually we need to start looking atomically at what's happening there. So again, remember that it's improper, so we need to look at that shearing and understand that, and then link that to the atomic displacement. So otherwise, really, we can't understand what's happening, and thus we can't make devices out of this. Okay, so we didn't even have a stiff file at the start. We didn't understand, okay, let's say the displacement goes this way, what does that result in polarization? So I went and luckily convinced Dr. Sinead Griffin at Lawrence Berkeley National Lab within the Molecular Foundry to do DFT calculations. So her experience is in improper ferroelectrics. And from her calculations, then now we're able to say, okay, if the atomic columns go a certain way, in this case, it's the copper columns that cause the main contributor to the polarization, then the polarization literally goes the opposite way. But also to confirm that experimentally. So we didn't just use STEM HADF atomically, we also used a STEM IDBC. And with that, then we were able to map out those lighter atomic columns as well. Now, long term, we realized we don't actually need those we don't need to understand those lighter atomic columns once we can confirm that they move in this way when the heavy atoms move in that way. So now we can move on and say, yeah, we're happy, experimentally links perfectly with theory. Great, let's move on. Let's make it more simple for ourselves. So yeah, so you can see then down at right at the bottom, that's really the most important, the STEM HADF. So for the rest of the talk, it'll all be in STEM HADF. And map out the yellow arrows, and on the left is a schematic there, is what is important, because what you get is up and down and up and down displacement of the copper columns in one direction, which is just going to cancel each other out. But overall, there's a displacement of the copper columns in one direction. So in this case, in the slide, the copper columns are overall moving in the direction that is left, but that means then the polarization is actually opposite. So 180 to that, so right. Okay, so we started off by saying this is great. We're able to move the domain walls under the electric field. We're able to say we know where what displacement means what. So we want to then look at this live of the whole field of view of what's happening when you apply a bias. So we started using the applied electric field of the STEM probe. And with that, then we used what is called differential phase contrast mapping. And I'd love to go through that in questions, but basically you take your STEM probe across, and then when you go across a certain domain, especially a ferroelectric domain, it should be deflected in a certain way due to either the polarization or the strain. And if you use a segment detector for your microscope, then you can say, okay, there's the beam went more in this segment or whatever segment it did go on. And then you get a whole field of view of going through that domain, the beam deflected this way, so either the polarization or the strain is in that direction. And then this gives us then this lovely colorful maps. This is a GIF of a series of scans, and you can see the domain walls moving under the STEM probe. And then we also started studying, okay, if we bring the STEM probe in a certain direction, it starts going even, let's say, more crazy. There's less control of the electron of the domain walls. But all of this is actually really interesting. We just need to start quantifying what's going on. And it does relate then back to the in-situ biasing holder, because perhaps we should apply our contacts in the in-situ biasing holder in certain ways so that we can form certain types of domain wall patterns. Okay, so then what we say, we take our DPC map of the overall FID lamella itself, and we say, okay, now we can, that domain wall, that would be really cool. That wall there is, let's say, an insulating wall or conducting wall or whatever you want to look at. Let's go now down to the atomic scale. So for this case, we started looking at 180 type walls, and all you need to understand what that is, as you can see in the yellow arrows, the polarization of the two domains meeting each other are 180 to each other. So at the start, because the arrows are pointing towards each other, then and the wall is between those at that angle, then we say, okay, it was in a highly charged state. So in this case, because the displacement, which are the yellow arrows, that means that it's a conductive wall because the polarization is the opposite way. And then you can, if you keep manipulating the beam direction, you can actually form it to go into a neutral state. And then you can flip it back again. So it's fully cyclical. And again, it's not just 180 type walls. We can also do this with a 90 type wall. So it looks like it's happening for all the different types of domain walls as well. And then as the kind of inserts there show, then we're able to actually quantify those shifts, and we're able to quantify what's happening at the wall, and then what changes away from the wall itself. So this then with in conjunction with Trinity College Dublin, so with Dr. Lewis Jones and Clive Downing, then we were able to actually get enough of, I suppose, spatial resolution as well, and then using Owen O'Connell's in our group. So Owen has new code put out, so you can find it at that link below there. So our TEM toolkit, so we're able to then map out this kind of displacement, because there simply wasn't code out there at the moment to also map out that displacement. This is really important because we want to understand how thick the domain wall is and what happens at it, and is how much of a change there is in the polarization from the wall and into the domain itself. And then also what's really, really cool, and this would be the next step for in-situ biasing, is also not just looking at a single wall. So in this case, it's triple junction. We can form all these cool, weird patterns. So in this case, then you're able to go from a triple junction to a vertex. And why this is really interesting is that you're able to then, I think hopefully in the right image, you can see you're able to get insulating walls and conducting walls all within the same region. And if I just flip the incoming STEM probe direction, then I'm able to then bring that back to a more neutral state again. And again, you can just keep cycling this. And as long as you don't damage your sample, so you don't give it too much beam current, then it is cyclical because you're not damaging it. Okay, so that's great. So we figured out the displacement, we figured out we could move the wall. We now know when we bring the STEM probe in a certain direction, what that results in the type of domain wall orientation. But it's still not a perfect, it's not a proper ferroelectric, it's still improper. And for this material at room temperature, it's directly linked to the ferroelasticity. So we wanted to then relate, how does that change in ferroelasticity directly link to the ferroelectricity and thus down to the atomic displacements? So we went to the experts at LBNL. So we talked to Colin Office and with Steve Zeltman and Benjamin Savitsky, and then using Ben and Stephen's Pi40 STEM, which is at the link below there as well. So the Pi40 STEM toolkit then is a software program they've written so that you can take these data sets, these 40 STEM data sets, and then get actually information out of it. So Eileen Courtney then within our group started processing that in conjunction with the NSTEM group. And now we're able to say, okay, when we take those 40 STEM data sets and we quantify the strain, does that relate directly then back to the atomic displacements and the shearing of the unit cell as well? And by using the combination of Pi40STEM and Owen O'Connell's TEM toolkit, we were able to say yes. So the atomic displacements and the shearing of the unit cell is related directly to the 40STEM measurements. Now we can start really using this. This is one example then. So we want to go looking at the dynamics. So in this case, again, using the STEM probe as the applied bias, we're able to then show that when at the start, when you don't have your domain wall, let's say stable, because you brought the STEM probe in at a kind of an odd angle, you can really see then the shearing, so the EXY is all over the place until it starts stabilizing. And then you, as you can see from the last frame, you can see then that each of those domains have a clear EXY measurements, and then also at the wall relative to the first two frames where it's a bit chaos. But it's very important to understand that, because otherwise we wouldn't be able to apply that back then to the ferroelectricity. Okay, so that's really great. So we're able to use the STEM probe. However, we want devices, and there isn't a device at the moment where you have a tiny little subatomic probe coming along and moving your circuitry around. So we started then using the in-situ biasing holder. So in this case, made of fib lamella again, put it down onto the MEMS chip. So this again is a for heating to biasing. And in this case, what was really interesting macroscopically, but also what related then back to microscopically or even atomically, was that when we saw with the STEM probe, we saw this kind of zigzag at the wall as it was moving. And again, you see that macroscopically as well within the TEM. And why that's really important is because the TEM illumination is parallel, thus you're not using the electron beam to move the wall, you're purely using in-situ biasing holder. But even with that, the in-situ biasing holder, you still get that zigzag. So it's not actually inherent to the electron beam, it's the material itself and the dynamics of the domain wall. So then you can start looking at a higher resolution, still really low res at this point, and you can start mapping out then what's happening at the wall. So you can see there's a change then in the type of wall and the type of polarization there. Okay, and then relating that then back to the work with Queen's University Belfast. So they saw that wall also had this kind of intermittent move and shake and bowing, which then when we go down to a higher, or when we go mag up, I suppose, we also see it's not just a round curvature, there's a zigzag in the wall itself. And we're also monitoring breakdown as well. So because also that's fun, but devices as well will need to understand what happens in that case if we do apply too much bias. And then we try to reuse that material as well. Okay, so then we did in December is brought the biasing holder over to Molecular Foundry at Lawrence Berkeley National Lab, and we conducted the exact same experiments because now we're confident, now we know how to quantify the strain. And then we also added that with in-situ biasing. So we're processing that data at the moment, and so I suppose watch this space because that will be the next publication coming out, where we're able to then not just watch what's happening with the domain wall movement, we're also able to relate that back directly to the change in strain when you bias. Okay, then it's not just biasing. So I think at the talk at the start of this section showed that going from a high temperature to the low temperature phase, that change. So from the cubic to the orthorhombic or pseudo-cubic, that's very important because that actually forms, that shearing forms the displacement, thus the polarization. But what we noticed in the in-situ heating experiments was that also macroscopically, there was actually a pseudo phase or an interphase between those two. And then from work with Professor Michael Carpenter at Cambridge, where at the exact same time, so that's good, we didn't tell each other what we were seeing, he also sees this. So there is some phase in between, but the great thing about TEM is that we're visually able to see that. And again, we couldn't have done that without using in-situ biasing holder and in-situ heating in this case. So then we repeated those experiments, the experiments here, also at 40STEM, and again, we're processing that data. So now we can relate directly that strain of what's happening at that kind of I suppose midpoint that we didn't actually know, that kind of quasi phase. So the conclusion and take-home message, I suppose, from this section is that in-situ electron microscopy really does provide a new platform, especially for ferroelectrics. So there's a lot of work on in-situ with other types of microscopy techniques, whether that's physical probes, so AFM and CFM and STM. But the great thing for TM is that you can get right down to the atomic scale. And for ferroelectrics, if all that's governing whether you get something conducting or not is a slight pico displacement, well then really you need to be able to use aberration corrected STEM. And then also for us, as well as combining that with 4D STEM, which I know a lot of groups now are using heavily. Before it was a lot of ferromagnetic groups, and now a lot of more people are starting using it for ferroelectrics as well. So acknowledgements, of course, we couldn't do a little bit of 4D STEM, now that we are doing it also at UL, but to get us going with the experts, thank you to the Department of Energy to fund the project with Dr. Colin Office and Dr. Jim Siston, and then also the second project, again, funded by the DOE with Dr. Sinead Griffin, because without DFT, we really couldn't have understood, let's say you get the displacement, but what does that mean in terms of polarization? Quinton Ramas at SaberSTEM, not only for its atomic resolution imaging in some of those slides as well, and also the electron spectroscopy. And then Dr. Lewis Jones and and then Clive Downing as well, for also not only the imaging, but also the processing of those images as well. So instead of doing much more low dose imaging rather than a very nice slow long image, and that meant we don't hurt the sample, and also that we're able to really quantify those displacements. Also Professor Ishi Bangert, our mentor and our head of our group at the University of Limerick, and thanks very recently to the Royal Society for getting me excited about this project, and I look forward to the next 5 years doing more in-situ biasing and also really heavily looking into these ferroelectric domain walls. So with that, thank you.
Right. Well, thank you very much, Michele, for a very interesting talk. It was a pleasure to listen to. So, Michele, for this this research, the coming 5 years that you're going to do, what are you hoping to find, and what kind of applications in the future do you envision for these with what you're going to discover in the domain wall?
So the first thing will definitely be strain engineering. We're looking at single crystals and making these fib lamellas, but if the strain is related directly to, let's say, the ferroelectricity and whether you get a conducting or insulating wall, then I think it's really important to start looking at thin film growth. So that's what I'll be looking at. And with that, then doing the in-situ biasing of thin films rather than just, let's say, the bulk crystal, because that really is what the device will be. I hope also to start getting more creative with in-situ biasing, so putting down my contacts in different ways, like let's say a 4-point kind of probe measurements as well, because I can start seeing now that you don't just you don't need to just study, let's say, the movement of a single domain wall. Also, you can form these like fourfold junctions and all these kind of exotic different types of junctions. Really, that some people are suggesting for other ferroelectric materials and ferromagnetic materials that could be these kind of quantum dot states, or for really exotic devices, really long term as well. And also speaking of ferromagnetics, to also look at, can we change the alloy composition, so change that metal and the way possibly it could grow it to also make it ferromagnetic, possibly. So that you get the ferroelectricity, the ferromagnetism, and then also possibly get the ferroelasticity. So getting all those kind of components to make some dream electronic device that the end user could write all the circuitry. That's the big goal.
All right. Wow, there's a lot of it opens up a lot of possibilities, and we will talk again in 5 years to see where your path has gone, because it can go all kinds of directions. I see that we have some questions coming in. The first one is, Yui Ding from TU Darmstadt. And so the question is, do you have any experience of in-situ biasing of ferroelectric ceramic materials?
No, we haven't actually done any ceramic materials yet. So that would be the answer to that. So no, nope.
Okay. Then, okay, thank you. Is the
Okay.
so Oana Andrea. So the question is, first of all, thank you for a very nice talk. So can you please tell me if you had any challenges in reaching atomic resolution when the sample was under voltage bias? And also, what is the ideal thickness of the FIB lamella for biasing experiments?
I'm lucky, it depends on what zone. So because I only need HADF and the unit cell is quite large. To be honest, I was very lucky that I did not need to have it really thin. For quantifying, let's say, the domain wall thickness, definitely sub 30 nanometers, which was the sample not on the in-situ biasing holder. So some of the images that were processed by Lewis. However, on the in-situ biasing recently that we did at LBNL, I'd say that sample is not much less than 80 nanometers, and then we're still able to get to atomic resolution as well. So for us, we're able to do the in-situ biasing atomically and then also the 4D stem mapping. But if I try, and I did try this, so I tried then the zone, which is the 110, but it's just, it's very difficult then. So then it needs to be much thinner. I think it's more that we're just very lucky that the zone that is easy for displacement mapping is a nice large, I suppose, unit cell through that projection. So I would say, yeah, about less than 80 nanometers and you're fine for the 100. For the 110, I had to thin it a lot more. It really needed to get down to, I would say definitely 50 nanometers, but less. And then the material itself is challenging for the copper chlorine because it's the complete opposite of brittle. It's very malleable, so you kind of get these bending contours. And although you can kind of avoid it, how much that causes issues with atomic displacement mapping, but to do the 4D stem strain mapping, if you have a bending contour, that's going to throw those measurements out the window. So it's an interplay between having it thin enough to get to atomic resolution, but also not having the bending contours, which is quite difficult for this material. I have done in-situ biasing with iron iodine borosite, and that's not as malleable, so it's just easier. So it really depends on the material. I think we did some in-situ biasing with I think it was lead titanate, and again that was easier just because it wasn't as malleable. That has its own problems, but it didn't have that issue. So I would say the main thing was that kind of just the copper chlorine was, I don't know, it was like milling glass or something amorphous. So that was the issue I had anyway. I don't know if that answered the question.
Yeah, I hope so too. Maybe, yes, we have a reaction. Thank you. And another question from Oana. Do you use just FIB or are you finishing in the NanoMill?
I was just using FIB because we can go down to 0.5 EV. So just because we have the newer FIB, for the in-situ biasing holder, for the images then taken not in the in-situ biasing holder, use the NanoMill just to get it pretty much more just to clean up any amorphous damage. But I do think if you can use the low voltage in the FIB, you usually avoid necessarily having to use the NanoMill for in-situ biasing. From what I've seen, I'm not saying for all materials, but from what I've seen, it seems like it's okay.
All right, so thank you very much for your answer. Now I want to give the microphone to my colleague, Jin, who also had a few questions for you.
Shelly, thanks a lot for the talk. Really great results. Well, I have a number of questions. I will start from the end. So you mentioned, Wesley, one of your samples is a fib lamella, and I'm just curious if you encounter any issues making like a working device on the fib, like using fib lamella, and if there are any like sort of tips and tricks to achieve that.
I think I hopefully, maybe I'll go back to the image. So that was the first time I did it, so Jin, where it was in-situ heating. But when I tried to bias that, I was being really silly. So I'm not sure if you can you see my mouse?
Yes, I can.
Okay, great. So
and I see the issue.
Of course, that was yeah, exactly, right? So that was the very first lamella we did the in-situ heating. But of course, if you bias it, and this is a platinum across the protection layer on the top, then I mean, you're just gonna get the flow of electrons across there, right? Your current is just gonna avoid what is an insulating material and just go across your lovely platinum layer. So then what I started doing, and I hopefully maybe the other slide might show that better. So yeah, so okay. So then what I did is cut here and then cut here. So this is where the platinum layer is up at the top. And the reason why I did that was so that whether, you know, plus or minus of course, the applied voltage, so that it would flow through the material and then up through the contact that way. That's what I did for the copper chlorine borosite, and it seems to work. I mean, that's what's worked so far. So yeah, I forgot. And I also did this with lithium niobate, which is a different type of ferroelectric, and that seems to work as well, much better. So definitely cutting those, otherwise you just get your current across your protection layer.
Okay, great, thanks. And but let's say, since you are interested in the effect of electric field, right? Like, do you need to make the contacts, or like, did you make the contacts to the between the lamella and the biasing electrodes on the chip?
Mm-hmm. Yeah, I still but I'm like, I mean, that would also be a good question also to go back to you about as well. It would be great not to have to put down those contacts. I don't know whether that's even possible or not. Just if you, because, you know, for the in-situ heating, normally what I would do is never put down any platinum and then just drop it down onto the chip and never apply any contact in the fib. So just come along and drop my lamella down. As one, that was the old way I used to do it, with a carbon protection layer. But I don't know what your experience is. I haven't tried to just drop it down or not use a contact between the fib lamella and the contacts on the MEMS chip itself. I don't know.
Well, if it's a ferroelectric, I usually don't contact, and then sometimes, well, let's say I don't contact the electrodes. So I do weld the lamella to the silicon nitride, but I don't contact specifically the lamella to the biasing electrodes. And another trick is actually you can use only one contact. Maybe, well, even if you contact to one of the electrodes, you don't contact to the other. And then that would be kind of the best thing.
Cool. See, I'm learning as well.
Yeah, since you have a really cool fib, probably you have also TEOS. Yeah. So potentially, let's say I wanted to always try. So TEOS is not conductive, it's not very conductive. So instead of using platinum, if you just wanted to weld your lamella to the chip, you can use TEOS.
Okay. Ooh.
Yeah.
I'm gonna talk to you before or after this.
Sure.
Thanks, Jin.
Yeah, thank you. Well, I have more questions. I'm not sure if there is time still. Olaf?
Yeah, we have 1-2 minutes. Yeah.
Okay. And then I have another question about the. Oh yeah, well, basically I have a number of questions, but maybe we should also talk afterwards. But so you right now, what you're doing in-situ biasing, and you say that, well, you basically well, you're driving domains, and the domains is basically they related to the strain in the material. So I'm just curious if you're following a path, because whenever you prepare a sample, from the preparation you introduce stresses there. So do you anneal the sample beforehand and then do biasing? Because usually the heating kind of helps release the stresses to go to sort of a ground state.
Yeah, so normally it actually kind of depends. So if I put the fib lamella in and I have, let's say, if I have, let's say, a charged wall, whether that's insulating or conducting or 180 type or 90 wall, then normally I would go straight into the biasing, purely because if I do the heat cycle, the worst part is that I could heat cycle it, and then the new pattern that forms doesn't form anything that's charged, like a charged type wall. And so then the biasing, even if I do the biasing, I'm just, I'd be moving non-charged walls. And really what I'm trying to do is investigate charged walls. However, if I make a fib lamella and then there are no charged walls in there, I'll just cycle it a bunch of times, and with luck, depending on the ramp, you know, like the drop down of the temperature, you can start forming, maybe sometimes you can form really interesting patterns. Yeah, so that's why I would do that. Really great to do some kind of making different patterns. Like I'd love to start kind of making patterns in the fib lamella itself. I know some people for ferroelectrics, like they actually, you know, using the fib in the bulk material, they make whatever, like a spiral or a square or something like that. And then let's say within that region that they've made a pattern, then they get these really unusual type of domain wall patterns or domain patterns. So that would be kind of the next step. But with the strain, the problem is that I can't identify a type of domain wall pattern in the bulk material because it's ferroelastic. The minute I do the undercut for the fib prep, that pattern is totally changed. So like, let's say I take my sample and Queens have done CFM mapping and say that's a conducting wall. If I then go try and then I put it in the fib and I say, okay, great, I'm going to go target that conducting wall, and I can see, luckily, you know, in the STM, I can see that bright contrast from the wall itself. The minute I do the J cut, it's gone. Okay. And so, yeah. So I can't. It's not like, you know, we make lamellas with the other type of ferroelectric materials. It's great. What is in the bulk is normally, luckily, what I've seen so far is what's in the fib lamella. But with this, I need to just pretend, you know, there's no point looking at the bulk material for this because, yeah, it's totally different than fib.
Okay, yeah. Clear. Yeah, it's a tough sample to trace.
Yeah.
I want to say a very, very big thanks to Michele. How was your experience? How was it to do the webinar? Oh, you're muted.
No, it was great, especially during the current situation. It's nice to have, you know, especially a live webinar. So it's really good. And the tricks gin as well. So hopefully, like, you know, improve some of the more new fib experiments and everything like that. So thank you for having me as well.
Yeah, thank you for presenting. It was the pleasure was all ours. So to everyone, I wish you a great day. Tomorrow you will get the email with the recording, and you can also reply to that if you want to get in touch with Michele. And we hope to see you in the next webinar. So have a great day. And that brings us to the end of this Nanotalk. To stay informed about upcoming webinars, I invite you to follow our social media channels, LinkedIn and Twitter. I also invite you to sign up for our monthly newsletter, in which we share interesting in-situ research and technological innovations. I want to thank you for watching and hope to meet you at one of our next webinars.